Hey class, welcome to video 2 of nuclear power. We're going to pick up where we left off in a sense. We're going to talk about how power plants use nuclear fuel in order to generate electricity in this segment. So one of the things we want to think about first is what exactly is that fissile material that is used in a nuclear power plant. So you see some choices here, and the actual correct answer to that is uranium. So most power plants that we see today use uranium for fuel. As far as how do we get that uranium, the answer to that is it is mined out of rocks. So when we look at the uranium that we get today, it is coming from mining, and what that means is the other problems that we learned about with mining are also going to be taking place. So acid production from sulfur, as well as groundwater contamination, runoff, etc. Those are all issues that are associated with the mining of uranium as well. When we look at where does it happen in the world, you see that the United States does mine some of its own uranium, but other countries are bigger producers of uranium than the United States will be. When you look at getting the stuff out of the ground, so we have to do all the processing that we learned about with mining, but on top of it, you're going to have the fact that you are dealing with a radioactive material. So you have to deal with the radiation that is produced. When we look at the uranium that you get out of rocks in the ground, most rocks on Earth that have uranium are going to have U-238. And U-238 is fissile, it's fissionable, but not fissile. And what that means is you can't get the chain reaction out of it. So you cannot use U-238 in a nuclear power plant. Only U-235 is the fissile form of uranium. That is the one that you want in order to run a nuclear power plant. It only accounts for 0.7 of all uranium on Earth, so that means once you mine the uranium, you have to go through a separation process in order to separate away the U-235 from U-238. How would you do that? Well, we know that the fundamental difference between them is mass, and so if that's the case, you can use something that will help to separate them based upon their mass, and that is called a centrifuge. By spinning it around at high speeds, what you will get is it will separate where the more dense material, heavier material, will react differently than the lighter material, and it will separate away from each other. It takes an awful lot of work in order to get it that way, and that's one of the difficulties and challenges of working with nuclear material. So you can concentrate it up to a level of 3 to 4% uranium-235, and that is sufficient to run a nuclear power plant. If you want weapons-grade uranium, that means enough to make a nuclear bomb, what they typically say is about 90% of U-235 is necessary for that. When you go to a nuclear power plant and you were to observe it from a distance, you would notice that you get these big towers and there's stuff coming out the top of them. And so we wonder, well, what is that stuff? As it turns out, it is water vapor. Water vapor is the main emission from nuclear power plants. You do not have carbon dioxide emissions. And so when we look at that, this is a reason why some people think that this could be a component of a good climate solution. So if we're thinking about reducing greenhouse gases to the atmosphere, nuclear could potentially be an important part of the solution. When you look at, well, do you still get some CO2 emissions? The answer is yes, because after all, you have to go through the mining process, and that uses fossil fuel equipment usually, so therefore you would potentially still have some emissions, but significantly reduced as compared to using fossil fuels for energy. When you look at how power plants are structured, what we see is that you would often have a containment building to contain the nuclear reactor. You wouldn't want it to go out of control and have nuclear material and radiation escaping, so you try to contain it. That works on a system where it keeps all of the radioactive material separate from the electrical generation equipment. So, basic process. Nuclear reactions happening in the core, and as a result it heats up water. That water then basically cycles through a pipe, which transfers its energy to a nearby pipe, which then heats up more water and then turns it to steam. The steam that goes from there is going to pass through these pipes right over in this section and eventually over to a fan-like structure, which we call a turbine. That turbine spins around rapidly. Along that turbine blade, we would have a magnet on there, and that's going to spin around in a coil of wire, and that's going to generate flow of electrons, which goes onto the electrical grid. So in terms of the steam that comes through here, it has to be cooled back down, condensed back into a liquid. It would still be a hot liquid at this point, but pumped back through the system where it can get heated up again into steam, and the cycle repeats. Now, in order to keep this as a condensing system, you have to cool it back down, and that's where this tertiary system comes into play. This now cools down the water so that you can get it to come back to a liquid and then pump it back through the system. But now this cooling water has been heated up, and that has to get cooled down before you can put it back into a river or a nearby water source. And that's where the cooling towers come into play. So those giant stacks generally just have hot water from the condensing system here, and it has to cool it down to a reasonable temperature before it can go back into the environment. So in terms of cost, it's difficult to assess the actual cost of nuclear power because they typically get a lot of government support. If somebody were to try to do this on their own, given all of the safety infrastructure that's necessary, it would be way too expensive to make nuclear power competitive. However, with government support, it can be a rather competitive solution. When you look at the challenges, we have three main things that I'd want you to know about: nuclear waste, nuclear accidents, and the proliferation of nuclear material. So when we talk about nuclear waste, the idea is that, okay, so U-235 is breaking down and releasing energy. However, there are byproducts of that breakdown, and those byproducts are also radioactive. But they're not capable of supporting a chain reaction, and therefore they're not going to be capable of running the power plant based upon their own radioactive decay. So the initial breakdown of U-235 is supplying the chain reaction and the massive amount of energy to run the power plant, but it turns into other things that give off some radiation, just not enough to maintain the power plant, and those are considered nuclear waste. They have to be gotten rid of, but they have to be done so in a safe way. So what do we do with it? So there was an idea of what to do, and that was to send it to Yucca Mountain in Nevada. The situation with that was it was partially built and perhaps even almost fully built when eventually it went to a vote, and it was very unpopular and people did not want it. And so as a result, the facility is built but not being used. So the main solution right now is nuclear power plants store their own waste underwater. For nuclear accidents, there have been two major ones that have happened in the world. One was in Chernobyl, and people often refer to it as just as Chernobyl. It happened in 1986, where one of the reactors, as they were going through a test of its capabilities, it ended up overheating. Most people attribute it to human error, that people should have made better decisions in the process of running this test, and as a result of those failures, ended up overheating the reactor and it ended up exploding. 47 people died at the power plant. Many people in the surrounding areas had to be evacuated and permanently be displaced. They cannot go back to their homes because it's just too dangerous to live in that region. It's hard to really know if you have what are the deaths that are caused by it. If somebody, let's say, was exposed to the radiation that led to mutations that caused cancer. That's a very difficult thing to establish, but some people have estimated that 4,000 or so deaths could be attributed to that. The other big nuclear accident is Fukushima in Japan in 2011, and we'll see if we can talk a little bit more about that one in class. For nuclear proliferation, the idea is when you have this nuclear waste, it can potentially be reprocessed into fissile material, and that could potentially be used to make a nuclear weapon. And so that one of the concerns about nuclear power is that you're generating this nuclear material which could be potentially used for weapons. People also talk about how you could just take the nuclear waste and make a dirty bomb where you just kind of have an explosion that scatters radioactive material, and then people would probably react to something like that in fear. So those are some of the concerns that we have regarding nuclear power and its proliferation. So what I want you to reflect on is, now that you've learned a little bit about nuclear power, what do you think? Is this something that we should be using? Is this part of our energy future? Is this something that we should not be using? I'd like you to put a little bit of thought into that and see what you're ready to talk about in class next time. Have a good one, and I will see you in class.